Hi, everyone. Welcome to this brief introduction to the state of climate science. We'll take a look at a little bit of climate data here, and we'll see a lot more of it later in the course. Scientific information about climate comes from lots of sources that fall broadly into the categories of observations of the world around us and modeling. People have collected and continue to generate multiple lines of evidence about how Earth's climate system works and how it changes. And when multiple lines of evidence, generated using all sorts of different approaches, pretty much converge to a coherent picture, our confidence in our understanding of the system goes up. We don't know everything, of course, since knowing everything is an impossible standard, and there's still plenty to learn, but we know a lot about how Earth's climate system operates. Here are a few observations. First, people have measured global average surface temperature over time, and that's gone up in the past century. Figuring out global average surface temperature is in itself a super challenging task, and several different groups of scientists using different approaches all end up with essentially the same story. As a second example, people have measured atmospheric CO2, which has also gone up since measurements began in the late 1950s. We have measurements of declining sea ice extent in the Arctic as time goes on, and we have measurements of sea level rise. These are all quite different measurements, yet together they form a logical, coherent story about climate, based essentially on how physics and chemistry work. There's virtually zero argument about the trends in these measurements. Here's another slightly more complicated set of observations. This animation represents changes in the distribution of summertime temperature anomalies in the Northern Hemisphere over time. So the word anomalies just means the difference between a measurement and some average. In this case, the average for comparison is average summer temperatures between 1951 and 1980. Temperature anomalies under the smooth curve in the gray area are considered to be within what we'd call normal for that time period. Values between -1 and -2 are considered to be colder than normal. Between -2 and -3 are very cold, and values to the left of -3 are considered extremely cold. Similarly, on the red side, values between +1 and +2 are considered hot. Between +2 and +3 are very hot, and to the right of +3, considered extremely hot. Over time, summertime temperatures have gradually shifted toward the warm end, with many more instances of what used to be considered extremely hot temperatures. And what these data show is that the probability of getting extreme warm events is greater than it used to be, and the probability of getting extreme cold events is lower than before. We also have observations and measurements of how Earth's climate system changed in the past. Here's the last million years, for example, which we'll look at more closely later in the course. Air bubbles trapped in ice preserve samples of the atmosphere at times in the past, so we can directly measure things like CO2 concentrations back through time as far back as the ice cores go, which is about 800,000 years. We can reconstruct temperature records using a wide variety of approaches, including things like the chemistry of sediments in the deep ocean, the types of organisms that lived in the past, the chemistry of corals, the chemistry of ice, and lots of other approaches. We can use these records from the past to learn how the Earth's climate system has varied before and how the parts are connected. To get a little practice looking at data, here's a question for you. You're going to find questions like this throughout the course for you to try as you go along. So here's the question. What's the general relationship between temperature and CO2 over time, according to these data? So read the two vertical axis scales and see what you think. So here, with these data that span the past million years, it's clear that temperature and CO2 are behaving similarly through time. Warm temperature and high CO2 happen at the same times, and cold temperatures happen at the same times as low CO2. This type of observation then leads us to deeper questions. By what processes are the two related? Does this pattern make any kind of physical sense? Is there evidence from some other source that either supports or refutes what we think is going on here? Also, from this type of information, we can get an idea of how much temperature changed in the past associated with what other changes to the system, like atmospheric CO2. This is a representation of a CO2 molecule. The physical behavior of carbon dioxide Its ability to absorb and emit infrared radiation coming from Earth's surface has been known for over 150 years. And well over 100 years ago, people actually started calculating the possible effects on global temperatures of human emissions of carbon dioxide to the atmosphere. What carbon dioxide and other greenhouse gases do in the atmosphere is very well known and uncontroversial. It's an old, well-established piece of scientific information. A more difficult question of interest, though, is how much warming do we get for an increase in atmospheric CO2? The reason this is more difficult is that an increase in CO2 sets off feedbacks in other parts of the climate system, involving things like water vapor and sea ice. And if we think about this question in terms of doubling CO2, in this example, going up from a pre-industrial value of about 280 parts per million to double that, or 560 parts per million, the best estimate is that global average surface temperatures are likely to rise about 3 degrees Celsius once various feedbacks occur and the system stabilizes at a new equilibrium temperature after this CO2 perturbation. This is a number that arises from numerous studies using numerous approaches, such as recent observations, geological observations, and climate modeling. Different studies will have different specific numbers, but in aggregate, the central value commonly comes out around 3 degrees per doubling of CO2 concentrations, and that estimate hasn't changed very much over time. The likely range of that number is probably somewhere between about 2 degrees and 4.5 degrees Celsius temperature rise for a doubling of CO2. And interestingly, we can pretty much eliminate really low values. It's highly unlikely to be less than about 1.5 degrees, but the high end is more difficult to constrain. If the climate system as a whole, with all of its parts and interactions, is just a bit more sensitive to a CO2 rise, we could see more than a 3-degree temperature rise. Some of the variability in the estimates has to do with aspects of the climate system that are not as well understood as CO2, and some of those aspects include the behavior of clouds in a warming world, the dynamics of melting ice sheets, the uptake of heat by the oceans, and what different aerosols do. Those are the little particles and droplets in the atmosphere. These are areas of active research, including both observational and modeling approaches. It's been more than 20 years now since the first assessment report from the Intergovernmental Panel on Climate Change. And over that time, scientific understanding has advanced and scientific evidence has expanded, with people examining multiple lines of evidence, both from observations and from models. The statements from each successive assessment report give us a sense of how scientific understanding of the role of humans in the climate system has evolved in that time. In 1990, the report stated that humankind is capable of altering temperatures. By 1995, they said that the effects of humans were discernible. By 2001, they were convinced that the preceding 50 years of warming was likely due to human activities. And by 2007, that was revised to very likely. Keep in mind that the IPCC, in seeking consensus, is by nature a conservative body. It cannot make outrageous claims. In fact, in most areas where the IPCC has turned out to be off track, it's tended to underestimate how fast and how much Earth's climate changes, such as in sea level rise and declines in sea ice extent. Among climate scientists, the consensus view that global temperatures are rising and that human activities are largely responsible is strong, and that's because the scientific evidence is strong. One example of this consensus is an analysis done by Naomi Oreskes of peer-reviewed papers published between 1993 and 2003 that were tagged with the keywords climate change. Of the nearly 1,000 papers analyzed, none of them disagreed with the consensus view. And later, similar analyses covering more recent publications have found similar results. An overwhelming percentage of climate scientists, about 97% based on surveys, agree that the evidence shows increasing global temperatures with human fingerprints. To summarize, ongoing work in climate science continually expands our understanding of Earth's climate system, both through observations and modeling efforts. Increasingly, detailed observations help us make better models, and models help us plan future observations. Some aspects of Earth's climate system are very well understood, like the interaction of greenhouse gases with infrared radiation. Others are less well understood and are areas of active research. We'll end with a question for discussion. Scientific evidence is one piece of information that helps inform policymaking. What role do you think science should play in decision-making? And why do you think that?